Okay, so everything we said previously was really just an introduction, okay, just an historic story. Now we're really starting the course. Now we're starting the real material. So the first topic that I want to discuss, and many of the things we're going to do in the first couple of lectures are going to be things you know. So it's going to be in part it's going to be a review. But that's okay, that's good. So the first thing I want to discuss is various sorts of numbers. So this n with a doubled leg here is a symbol for what are called the natural numbers. And what they are is all the numbers 1, 2, 3, 4, etc. So these are called the natural numbers. And there's a new symbol here, these squiggly things here, okay? And what they denote is a set. So n is the set of all the numbers 1, 2, 3, 4, etc., which are numbers with which you count apples, right? And you've all known these numbers since you were 6 months old, right? Nah, 2 years old, right? Well, okay. And then you went to daycare or to kindergarten or whatever, and you learned formally about these numbers, and you counted apples, and you maybe even learned to add 2 plus 3, and the bright kid said 5, right? And maybe you even learned to subtract 5 minus 2. Good, good. And then one kid said, how much is 2 minus 5? No such thing as 2 minus 5, right? But then somebody told you, well, maybe there is such a thing. And this is denoted by a z with a double leg, and this is called the integers. And the integers is the set of all these natural numbers, 1, 2, 3, etc., but also 0, which is a very, very important number, and also all these negative numbers, -1, -2, -3, etc. And now it does make sense to ask how much is 2 minus 5. 2 minus 5 is -3, right? And this is not something in somebody's mind. This is a very realistic thing. For example, if you go to the bank and take a loan, then your assets are minus $1,000, right? Do you agree? So it does make sense to discuss these numbers. The next group of numbers that showed up sometime in your life, maybe these even showed up first, I don't know, are called the rational numbers. Q is for rational. And this is the set, remember this denotes a set, of all numbers of the form m over n. All these fractions are quotients. Q is really for quotients. So it's all the numbers, so look at the notation a minute, the set of all numbers of the form m over n, such that m and n belong to the integers. And one more thing that I have to make sure. Right. N cannot be 0, because we can never divide by 0. It's not defined. Okay? So these are the rational numbers. And whereas here it didn't make sense, for example, to say, what is 3 divided by 2? Now it does make sense. Okay? So these are the rational numbers. But there are more numbers than that. Okay, so the number system in which we're going to be working mostly throughout this course is called the reals. R is for reals. And I'm going to cheat you a bit now. So I'm not going to define them very precisely. I'm just going to tell you what they are. Defining them precisely is beyond the scope of this course. Okay? So it's all the numbers x on the real line. Okay? So all the numbers x such that x is between infinity and negative infinity. Okay? The entire real line. Okay? Now, let's introduce a bit more notation. So when I write something like this, 3 over 4 can you read that? It says 3/4 does not belong to the integers, right? Can you understand when I write this? The natural numbers are contained in the integers. So this lengthy C means contained. Okay? And the interesting thing in this story, which I'm going to discuss a bit more, is the fact that the rational numbers are not everything. So there are real numbers which are not rational. So writing that would be Q is contained in R, but is not equal to R. Can you read that? Okay, so we're learning a new language, a new alphabet, new symbols. Okay? So, and this fact, in fact, this fact was known quite a while back. Okay? So, even the ancient Greeks, okay? Do you know have you heard of Pythagoras? Everybody? Okay, so what did Pythagoras say? Pythagoras said, if you take a triangle for which one of the angles is precisely 90 degrees, right? A right angle. Then, okay, so let's call this A, B, and C. What did Pythagoras say? Right. So Pythagoras said that if this is A, this is B, and this is C, then A squared plus B squared equals C squared. Right? So if you so this is Pythagoras. Should be a capital P. Do you agree? Now what if you take let's just draw another triangle. What if you take a triangle? This is very easy to do. Take a right triangle where these two edges are precisely 1. 1 meter and 1 meter. And call this C for a minute. What is C? So C squared has to be 2, right? So this C satisfies that C squared equals 2. And we have a notation for that, right? We call C, what do we call it? Square root of 2. Do you agree? So do you agree that this number is as real a number as can be? I mean, I can draw a yardstick. Well, it's not going to be a yard, but I can take a line whose length is precisely root 2 meters. It's easy to do, right? And the claim is that this number, the square root of 2, is not a rational number. It's a real number, but it's not a rational number. It cannot be written as the quotient of two integers. Okay? And this is going to be the first theorem that I'm actually going to prove for you. Okay, one second. So let's write it as a theorem. Theorem. Root 2 does not belong to the rationals. Okay? Proof. Now this fact is not such an essential piece of knowledge and let alone the proof. But this is, I want to demonstrate techniques of proving things. I want you to learn how to prove things, okay? And this is going to be our first example. Question?
Just in terms of, how can we write not equal to for the natural integers?
Why didn't I write n contained using this?
Yeah.
I could. It would be just as correct. Okay, so yeah. The natural numbers are contained in the integers, but they're not equal. Okay? Okay. So let's prove this fact. So the way I'm going to do it is called proof by contradiction. Okay? I'm going to assume that root 2 is rational. If, using this assumption, I can deduce by logical steps that something which we know for a fact of life is suddenly not true, so if I can do this and suddenly get to 1 equals 2, that means that my original assumption was false. Okay? If I get to a contradiction, that means that my original assumption was false. Do you agree? Okay, so that's what's called proof by contradiction. So we're going to assume that this is true, and somehow we're going to encounter something that cannot be, some contradiction. Okay? And if that cannot be, it means our assumption was wrong, which means that this is the true case. Okay? Clear? So let's do that. So if root 2 is rational, okay, okay, fine, let's leave it like this. Then there exist m and n, both integers, such that n is not 0, and this root 2 guy equals m over n. That's what it means to be a rational number. That was the definition of the rational numbers. Right? Now, let's just for a minute look at this set of rational numbers. Do you agree that writing a rational number is not unique? You can write 3 over 3 or 2 over 2, and that's the same number. Do you agree? Or 6 over 4 and 12 over 8. That's the same number, right? So if m and n have a common factor, we can divide m and n by it and get the same number in a more reduced form. Do you agree? So whenever we get a rational number, we can always reduce it until it's at the most reduced form. Okay? Do you agree? To the point where m and n do not have any common dividers. Do you agree? Okay. So we wrote root 2 as m over n, and if it's not in reduced form, reduce it. So take it in reduced form. We can always do that. Right? Okay, so I'm just going to assume it. Root 2 equals m over n, and m and n do not have common factors. Okay, so this is reduced. Let's write that. Reduced. Okay? Okay. Now let's start doing logical steps and see where we get the contradiction. So, root 2 equals m over n. That's our assumption. It follows, do you know this symbol? An arrow with a double line here. This symbol means it follows. So if root 2 is m over n, it follows that 2 equals m squared over n squared. I squared both sides. If at any point I write a step that you don't agree with or need a further explanation, just let me know. Okay? Okay. So from here it follows that m squared equals 2n squared. Okay, so when I write this right-hand side is divisible by 2, right? It's 2 times something. But that means that the left-hand side is divisible by 2. Do you agree? So m squared is divisible by 2. What's the word for divisible by 2? Even. So it follows that m squared is an even number. Do you agree? Everybody? Say yes.
Yes.
Okay. But if the square of a number is even, then the number itself must be even. Because if m was not even, if m was odd, then m squared would be odd as well. When you multiply two odd numbers, you get an odd number. Do you agree? So m itself has to be even. But if m is even, that means that m is 2 times something, right? M has a factor of 2 in it. Then m squared already has a factor of 4 in it. It can be divided by 4. Do you agree? So m squared is divisible by 4. Do you agree?
Yes.
Okay. But m squared was 2n squared. So this means that 2n squared is divisible by 4. But if 2n squared is divisible by 4, then n squared itself is divisible by 2. N squared is even. And once again, if n squared is even, what does it mean? Then n itself is even.
Explain again why, because n squared is even and even.
If you take an odd number and multiply it by another odd number, you get an odd number. Okay? Do you agree to that? So if m were odd, m squared would have to be odd. But m squared is even. So m itself must be even. Okay? Is the logic clear? Okay. So this completes the proof. We found a contradiction. Where's the contradiction? M is even. N is even. that means they have a common factor. They're both divisible by 2. But we started out by taking them without a common factor. That's a contradiction. Do you see that? Does everybody see that? So this is a contradiction, and if you get to a contradiction, it means that your original assumption was wrong. Okay? So this is a contradiction, and that completes the proof. Sometimes at the end of a proof, we're going to put a little black square. Yeah. And this little black square just means end of proof. Sometimes you'll see it in books written QED, which is, right, it's a Latin abbreviation. But this little black square was introduced by a mathematician called Halmos, and he was very famous, and people just happened to like this. So now everybody uses it, and it's even called a Halmos. So think of the honor of having a little black square named after you. And that little black square appears in every paper in mathematics. I mean, even Cauchy is not mentioned in every paper in mathematics, right? But Halmos is. I think that's a big honor. Okay, so what we just proved is that there exists a number, a very real number. It can be easily, you can easily draw a triangle whose edge is root 2, but that number is not rational. Okay, so the rationals are not everything. There's more to it, and we know more numbers that are not rational. Can you give me some? Right, pi is not a rational number. More? E is not a rational number. If you don't know what E is, we'll discuss it a bit later. Okay? And many, many more. Okay? So I'll answer questions in a second. Okay? So so there's a question here which should come to mind. How many rational numbers are there? How many reals that are not rational, sometimes called irrational? How many irrational numbers are there? If this is the x-axis, and where am I? Here. If this is the x-axis and I put my finger on it, what are my chances of landing on a rational number? What are my chances of landing on an irrational number? Okay? Is there like an interval in which all the numbers are rational? Is there an interval in which there is no rational number? Okay, those are interesting questions, and the answer to them is the following remark. For any x and y in R, for any two real numbers on the real line, let's assume, okay, one is going to have to be smaller than the other, so let's call x. For any x less than y in R, What? What did he say? Okay, so for any x less than y in R, any two real numbers, there exists a q in Q. Who's starting to sweat? Can you read through this? It's not that hard. It's just new, right? So let's read it again. For any x less than y belong to R, so for any two real numbers, there exists a rational number such that Q lies between x and y. I'm not going to prove that. Okay, we're not going to prove it. We're going to just take it as a fact. And in fact, it's true it's also true if you take an irrational number. Okay? So this is called the density of the rationals, which means that the rationals and the irrationals are kind of blended in between each other, but it's not true that there's a rational and irrational, a rational and irrational. That's not true. They're just so intertwined and intermingled that take any two numbers, there's going to be a rational number between them. Take those two numbers, there's going to be a rational between them. Take those two numbers, there's going to be a rational. You can cut it and cut it and cut it as far as you want. There's always going to be, no matter how small the interval is, there are going to be rational numbers there and irrational numbers there. So this is something that takes getting used to, like many things in this course. Okay, so you cannot, for example, find a region, an interval, where you only have irrationals or only have rationals. Okay? Questions? Yes?
I'm sure it's simple, but I didn't get the conclusion of that proof about the root 2.
So did you follow all the little steps?
Yeah.
Okay, so whenever you see a proof has two points of view that you have to try both. Okay? And to understand both. So one is from a distance of about this far. And from a distance of about this far, all you can do is trace step by step and agree that each step is correct. Okay? But then what you have to do is take a long step back. There's a step here. I don't want to fall. There we go. And look at it from a distance and see that you understand the whole argument. What did we do here? What just happened here? Okay? So I'm going to leave it to you to follow the little steps and make sure that you understand them. The overall picture was, we said, okay, if root 2 can be written as a rational, a quotient of two integers, take it in reduced form, and then play these games, which stem from squaring it and getting this 2 factor here, and suddenly you see that both these factors have to be even. But this was a contradiction. You reduce them. They're not both even because they're in reduced form. They don't have any common factors. And magic, they do. That's a contradiction. That cannot be true. So root 2 cannot be a rational number. Okay? Yes?
In proof by contradiction, do we have to explicitly say what the contradiction is, or it's enough to just say it's a contradiction?
You have to say, where do you see the contradiction? Yes. Okay? Okay, so this fact is called the density of the rationals. And we're going to use this fact and this sort of idea throughout. Okay, we're going to rely on that these integers and these rationals and irrationals are just everywhere. Both are just everywhere, and it's something you have to get used to. Another remark, and here I'm not going to add any details because I'm really assuming that you know this stuff. And if somebody is not sure of stuff, he can come later and ask me. R, maybe the name you don't know, maybe the word I'm going to use you don't know. R is a field. What does it mean to be a field? It means that the various laws that you know hold. For example, commutativity. If you do A plus B, that's the same as B plus A. You all know that, right? Right? You have to say yes now.
Yes.
Thank you. If you do A times B, that's the same as B times A. You know that, right? There's the distributive law. If you do A times B plus C, that's the same as AB plus AC. All those kind of rules hold. You know them. You've been working with them forever. These are good old numbers. Okay, and all these laws hold. The reason I'm pointing this out is that not everywhere, not everything is a field. You'll encounter later in your studies things, some of them you already know, but you haven't thought of it, that are not fields. Okay, but for us, the numbers are good. We can always multiply, it doesn't matter in which order. We can introduce parentheses, and it doesn't matter. So a plus b plus c is the same as a plus b plus c, whether you add a plus b first or whether you add b plus c first. Right? So all these things, I'm assuming you know. Okay. Okay, so, yeah. Okay, let's stop now. I know it's a couple of minutes early, but I don't want to start a new topic. So in the next lecture, we're going to continue this line of introduction and collecting as we go along more notation, more symbols, more terminology, and more techniques, seeing various small things and gradually building up to starting the real material. Okay, so thank you.